Welcome to Maths with EJD. In this video, I'll be talking about integration of vectors and integration of vectors involves applying integral calculus to vector functions. Of course, if you're new to integration, you can check my playlist on basic calculus. I think from lesson 13 or 14, I started talking about integration. Okay, so integration of vectors involves applying integral calculus to vector functions, basically. So this process is essential in fields like physics, engineering, where vector fields describe quantities like force, velocity, and electric and magnetic fields. So integrating these vectors can yield important results, such as the work done by a force or the flux of a field through surface. I guess I want to write all that. So this process is essential in fields like physics and engineering where vector fields describe quantities like force, velocity, and electric and magnetic fields. Okay, integrating these vectors can yield important results, such as the work done by a force or the flux of a field through a surface. Okay, so let's talk about let's have the definition. Let's define the integration of vectors. So definition. So again, vector integration is the process of integrating vector functions which can be functions of one or more variables, Then, of course, we talk about dimensions, right? So, for instance, in one dimension, so when we have just x in one dimension, integrating a vector function, might simply involve integrating each component of the vector, with respect to the parameter, say x. So this is more or less like the normal thing we know in normal integration, except that here you're talking about vector components, or we are talking about vectors, right? So, but then what if you have multiple dimensions, like two dimensions or three? So in multiple dimensions, I always have this issue with whether it's dimension or dimension. So in multiple dimensions, vector integration, that's like in 2D, 3D, in multiple dimensions, vector integration includes more complex operations, such as line integrals, line integrals, very important, and surface integrals, line integrals and surface integrals. So really important things to talk about. So that takes us to the next part where we talk about line integrals, and work done by a force field, So, I mean, this is, of course, arising from the place of talking about integration of multi-dimensional vectors. So line integrals and work done by a force field. So first off, a line integral, which is actually the same thing as a path integral, is an integral where the function to be integrated, where the function to be integrated is evaluated along a curve. In vector calculus, of course, vector calculus is all these places where you talk about differentiation of vectors, partial differentiation of vectors, and integration of vectors. So in vector calculus, line integrals can be used to calculate the work done by a force field when moving an object along a specific path. Okay. So, since we are still talking about line integral, right? Let's give a kind of mathematical definition. So let's say definition again under this. So for a vector field, f of x, y, and z, which is equal to f1i plus f2j plus f3k, like in 3 dimensions. So the line integral of f, of course, f is a force. The line integral of f along a curve C, parameterized by r of t, which is equal to x of ti, because this is vector, y of t j plus z of t k. Okay, from time equals a to time equals b is given by this. So line integral along the curve C is the dot product of F and the change in the positional vector R. And that is the same thing as integral from A to B, along the curve now. So that is F of R of T. So the force is a function of the position of T multiplied by the derivative of the position vector, that's R prime of T dt. So this is how that goes. And then we have the components. We have to explain the components. So we say where f of R of T, f of R of T represents the vector field, evaluated along the curve. Forget this is R, evaluated along the curve. Then we have R prime of T, right? R prime of T is the derivative of the position vector. We talked about position vector in one of our previous videos. Is the derivative of the position vector R of T with respect to T, that's time. Okay, then we also have dr, which is R prime of T dt. Okay, because dr dt is R prime of T. So dr dt is R prime of T. So it means that dr alone is R prime of T dt. Is actually is the differential. It is called the differential of the position vector along the curve. And that goes. So let's take an actual example that will involve, some calculations. All right, let's have this. Consider a force field. Consider a force field f of x comma y, which is equal to xi, because this is a vector, xi plus yj, and a curve C, should we say that's a vector too? Let me just say C, right? And a curve C defined by the parameterization R of T equals Ti plus T squared J, like that. So where T ranges from 0 to 1, So if we have this, right, to actually calculate the work done, right? So to calculate the work done, what do we do? First thing, so let me just call that step 1. Let's say step 1, we find R prime of T. That's the derivative of the position vector. Of course, we know that R of T itself is Ti plus T squared J. So that simply implies that R prime of T is equal to, differentiate T with respect to T, that's 1, right? So you just have, okay, well, we can say that's d dt, right, of Ti plus T squared J. Okay, that's, you want to differentiate that. So differentiate T with respect to T, that's 1 times I. So you have just the I left. Differentiate T squared, you get 2T. So that's 2TJ. That's the derivative. So you have that. Then step two. So in step two, you evaluate f of r of t, f of r of t. So to do that, we have f of r of t, that is simply f. Okay, the f itself originally is xi plus yj, right? So it is in two dimensions like that. And from the position vector, this is as good as x, and this is as good as y. Okay. So you have xy, so that we just have exactly that. So f of r of t will simply be ti plus t squared j, just like what we have right there. So the next thing is the step three. We compute the dot product. Look at the formula again. It's like we want to assemble this formula. This is what we are working towards. So we have this, now we have this. So we can do the dot product of the two before we integrate. So step three is to compute the dot product. Compute the dot product. So to compute the dot product, right, we have f of r of t dot r prime of t, and that is f of r of t, just like what we have now, is ti plus t squared j, then dot r prime of t. R prime of t is this, that's I plus 2tj, I plus 2tj, so I plus 2tj. And for dot product, we already know that ti and I can go together, so that's like multiply their coefficient. So it's more like saying t times 1 I, the coefficient of I here is t, the coefficient of I here is 1. Then that added to t squared, this multiplied by 2t, then of course j, so that we have ti plus 2t cube j. So that is the dot product for that expression. So now we can integrate this. That is step 4 now. Step 4. Okay, yeah, I was consistent with step 3. So step 4 is this. Integrate over the given range. Integrate over the given range. Integrate over the given range. So now we have what's that thing again? That's like f dot dr along the path C. So that is f dot dr, integral of this along the path C. That's simply equal to integral from A to B, integral from A to B of all that. Okay, so that's integral from A to B of f of r of t, like that, dot r prime of t dt. Okay, so here we already know, we know this. In fact, we have done the dot product. So the whole of this is the whole of this, and then we know our a is equal to 0, our b is equal to 1. That's talking about the time. So that's time ranging from 0 to 1. So this is simply equal to integral from 0 to 1 of that ti plus 2 3 squared. Okay, yeah, it's dot product. Sorry, I forgot that. This is going to be I dot I, and this is j dot j, and I dot I and j dot j are simply 1 each because they are unit vectors. So the dot product is actually t plus 2t cube. Sorry. So for dot product, you get a scalar quantity. So you can revisit vector operations. That second video, I believe, that takes care of that. So we have t now plus 2t cube dt. So then we can, so it looks like normal thing to integrate now. So here to integrate t raised power 1, that t is t raised power 1, so that's t squared divided by the new power of t. Then the next one, you have 2t, 3, add 1 to that, that's 4 divided by the new 4, and that has to be evaluated from 0 to 1, and that is okay, like I like to do, this is t squared over 2 plus t4 over 2 again from 0 to 1, and that's like you have, so you can split it apart, or better still, you can have half t squared plus half t raised power 4 from 0 to 1, okay? So that we can have half t squared from 0 to 1 plus half t raised power 4 from 0 to 1. And that is half into t squared, that's 1 squared minus 0 squared, plus half into t raised power 4, that's 1 raised power 4 minus 0 raised power 4. So that, of course, all these are zeros. So we have half into 1 squared is 1 plus half into 1 raised power 4 is also 1. So we have half plus half, and all of that is 1. So we can conclude that thus the work done by the force field, F, along the curve C, is 1 unit. That's 1 unit of work. I think work is measured in, I think, joules or something like that. So that means 1 unit, 1 joule unit or something, or that. So that's how that goes. So that brings us to the end of line integrals and computation of work done by a force field. So that takes us to the third part of integration of vectors, which is surface integrals. You know, we said that integration in multiple dimensions leads us to line and surface integrals, and they have application. So line integral has application in the area of work done by a force field, whereas surface integral has something to do with flux. So we saw the idea of flux under I think that must have been, is it divergence of a vector or so, or something like that? So, you know, we talked about gradient. Yeah, that must have been divergence for sure. So you're probably going to see something like that coming up under surface integrals and flux. So, you know, we talked about line integral, now we're talking about surface integral. So a surface integral calculates the integral of a scalar field or a vector field over a surface. So we're talking about surface. So the other one is along a curve for line integral, but here it's over a surface. So this is 2-dimensional for sure. So you're going to have x and y coming together. Unlike the only you just having x or t under the underlying integrals. So here, for a vector field, a surface integral represents the flux of the field, through the surface, which is a measure of how much of the field passes through that surface. Okay. So if you want to know how much of a field passes through a surface, you have to do surface integral. All right. So let's do a definition of this idea. So say definition, or I guess I can change at this point, right? So definition. So for a vector field, f of x, y, and z, the flux through a surface S, is given by, so now it's double integral on the surface. No, not along curve now, on surface. So that's over this surface now. So we have the F, the force field, multiplied by the vector normal, as that is said to be. So I don't know if I should give it a vector sign. I think that's better. So where so you see double integral now, because we're talking two surface, we're talking surface which is two-dimensional. So where ds is equal to unit vector multiplied by ds itself. So that is actually is a vector. It's a vector normal. It's a vector normal to the surface element, with magnitude equal to the area of the surface element, that is ds. Okay, so this is some kind of vector thing. So you have the normal vector here. So this is ds now. It's the surface element ds right here. Okay, so having said that, of course, we have the unit vector. Okay, this should be, I think this is f dot, let me see something. Okay. Okay, yeah, that's fine. So you see n is coming up here. So that n cap actually. So let's say n cap is the n. Should it be n cap, or, well, any sign to show that it's a vector in short? So I use a cap here. So n cap is the unit normal vector, to the surface. All right. So now if S is parameterized, by R, which is a vector now, which is a function of u and v, and that is x uv. You know, we are talking two-dimensional now. So that's x uv in the direction of I plus y uv in the direction of j plus z uv in the direction of k. So the surface integral can be written, you know, we already have the surface integral written in this particular way, right? But now this is us trying to expand it once we have a parameterization for S. So instead of having the S that way, right? Then we have R coming into the picture with two variables, with two dependent variables. So it can be written as, okay, it can be written as, of course, double integral along on the surface S with the force field multiplied by, so instead of having n cap ds now, so you have R differentiated differentiated with respect to u, multiplied by R differentiated with respect to v. That's partial differentiation now. Then you now have du dv, because you have those two components So again, where are you? Where are you? So these r's are vectors. So where are you would actually be partial r, partial u. That is u differentiated with respect to u, r differentiated with respect to u, and rv is partial r, partial v. That's partial differentiation of r with respect to v. So these are partial derivatives. These are partial derivatives, partial derivatives, partial derivatives of the parameterization, of the parameterization. Okay, so now we have RU cross RV. Okay, RU cross RV is actually the cross product, given a vector normal to the surface. So it is the cross product given a vector normal to the surface. Now, see this here, that this is actually ds, which is a vector thing. But if you break it down here, so you have the vector normal to the surface multiplied by just ds. That is not the vector. Now, that is the surface element. Now, some kind of scalar, because you have the n cap, which makes it a vector by when you multiply that. All right. So with this in place, let's take an example. Let's take an example, and I think it's time to change. So we have this, that okay, we want to consider a vector field. Consider a vector field f of x, y, and z, which is zi plus yj plus xk. Okay, now this does not follow the conventional xyz we've been using. So, but we just know the ij, we know ij and k normally are in the directions of x, y, and z. So we have this, right? And okay, we have the force field, and a surface, and a surface S, which is the upper hemisphere, upper hemisphere, hemisphere of the unit sphere, the upper hemisphere of the unit sphere, x squared plus y squared plus z squared equals 1. Oriented outward. Oriented outward. Okay, so this is what we have now. So we have a force field, and then we have its parameterization oriented outward, the upper hemisphere of a unit sphere, which is usually given as x squared plus y squared plus z squared. Okay, so for us to find the flux associated with this, right? So just say, okay, I guess I can change to find the flux, the flux associated with this. So we have to take certain steps. The first step is the parameterization. So for the first step, we have to deal with the parameterization. So step one, parameterize the surface. Parameterize the surface. Okay. So it's more like defining a function for the surface for easy handling. So here we use spherical coordinates. We use spherical coordinates. You know, you have the Cartesian coordinates normally. That's the XYZ axis. So here we are talking about the spherical coordinates for the upper hemisphere. For the upper hemisphere. So since we are talking about spheres, right? So that's where spherical coordinates comes in. So if we do that, it means we have, instead of RUV, then we have R theta phi, r theta phi, and that is sine phi cos theta I plus sine phi sine theta j plus cos phi k. So that's how the spherical coordinates go. So you have sine, cos, sine, and cos alone. So sine phi cos theta I plus sine phi sine theta j plus cos phi k. So now where 0 lies between, theta lies between 0 and 2 pi. So where 0 is less than or equal to theta, less than or equal to 2 pi. On the other hand, 0 less than or equal to phi, less than or equal to pi over 2. So that tells us that theta lies between 0 and 2 pi, whereas phi lies between 0 and pi over 2. Of course, 2 pi is 360 degrees. So theta is defined for the whole 4 quadrants. If you refer to my playlist on trigonometry, whereas phi lies between 0 and 90 degrees. So phi is only defined in the first quadrant. If I can give a kind of picture of this, right? Let me try to do that. Okay. So we have this, right? So let's say theta is defined everywhere. Theta is defined everywhere. So you have theta everywhere in these 4 quadrants. Okay. So that's where you have theta defined. But then for phi is defined only in this place. So you have an overlapping happening there. So you have phi here, whereas you have theta in this whole place like this. So that's the idea here. So that we can, so that we have parameterized now using spherical coordinates. So this is an expression that will be useful for us. Then we go to step 2. We compute the partial derivatives. Step 2, compute the partial derivatives. Compute the partial derivatives. So, of course, that should be, normally it should be r and r, but now we have r as a function of theta and phi. So it means that we have to differentiate this with respect to theta and differentiate with respect to phi respectively. So, okay, I guess I need to let me write that down again. We have r theta phi equals sine phi cos theta I plus sine phi sine phi sine phi sine theta j, sine phi sine theta j plus cos phi k. So that we now have, so this simply implies that r sub theta, that's partial r, partial theta, partial r, partial theta. So we are differentiating with respect to theta now. So sine phi is constant. So differentiate cos theta here. So that'll be differentiate cos theta with respect to theta. That's minus sine theta. So that means everything is minus sine phi sine theta I. Then here differentiate theta, right? We are differentiating theta. Differentiate sine theta, you get cos theta. So that will be plus sine theta sine phi cos theta, that is, then in the direction of j. Since we are differentiating with respect to theta, so if you differentiate cos phi with respect to theta, that will be 0 because there's no theta in that expression. So that is r theta. Then we also have r phi. R phi, now we're differentiating with respect to phi. Partial r, partial phi. That is equal to differentiate sine phi with respect to phi. You get cos phi cos theta I. Then for phi again, differentiate sine phi with respect to phi. So we also have plus cos phi sine theta j. So that's cos phi cos theta plus cos phi sine theta j. Then differentiate cos phi with respect, differentiate cos phi rather, you get minus sine phi in the direction of k. So those are the partial derivatives. So the next thing we want to do is to compute the cross products. Step 3. compute the cross product, compute the cross product, r theta cross r phi. That's the next thing to do. That simply means that r theta cross r phi is equal to, of course, I j. Let me give some space because this is quite something. So I j k. Then for r phi, right, in the direction of r, you have minus sine phi sine theta. So you have minus sine phi sine theta right here. Then for j up there, we have sine phi cos theta, sine phi sine phi cos theta. And then under k, we have 0 for r. So there's nothing in the direction of k here. Then for r phi, so we have this, and this for r phi. So this is cos phi. That's cos phi cos theta. Then for j, we have cos phi sine theta, cos phi sine theta. Then lastly, we have minus sine phi, like that. So then we can calculate the determinant. So of course, this is about determinants, like we already know. So this will be, so this is equal to, as usual, we do this normal thing. So if you are for I now, okay, yes, I should just use this. So I into, so cross out the row, cross out the column. So you have sine theta cos phi. So you have this multiplied by this minus this multiplied by this. So sine theta cos phi times minus sine theta, that's actually, so let me do it one after the other. So sine theta cos phi times minus sine phi. So that is going to be minus sine squared phi cos theta. That means, sine phi times sine phi is sine squared phi. This minus is there, so cos theta remains. Then minus cos phi sine theta times 0, that is simply 0. And that goes. Then we have, let me use this kind of scaling. So you have j now into, so this line goes, this line goes. Now cross out, okay, yeah. So cross out the column of j and the row it belongs to, so that we have, okay, this can also go. This can go now. So what do we have? So you have minus sine phi sine theta times minus sine phi. So that is going to be, minus and minus is plus. So we have sine squared phi sine theta minus cos phi cos theta, cos phi cos theta times 0. That is simply 0. So with that done again, we can go to k. So don't forget, this is plus. We've done this a number of times. So this is plus minus plus as usual. That's why we have plus here. Oh, okay. Thankfully, thank God I do that. So now I remember this should actually be negative. So plus minus plus. Then lastly, we go to k. So we have plus k into, so cross the column, the row, cross the column. So multiply this by this. So minus sine phi cos phi sine minus sine phi sine theta times cos phi sine theta. So that's going to be minus sine phi cos phi, then sine theta times sine theta, that's sine squared theta, all that minus what we have here. So that'll be sine theta, sine phi cos squared theta. So that is sine. So that's minus sine phi cos phi cos squared theta, like that. So sine phi cos squared theta. So now we can tidy this up and see what we get. Let's try to do that. This is seriously lengthy, but it's okay. We keep moving. Okay, so now we're still talking about r theta cross r phi. So, and that is the evaluation of this now. So we have, so if you put all this together, we have minus sine squared phi cos theta I. Then here, minus sine squared phi sine theta j. And lastly, we have, I think, can we factorize something here? I believe so. Okay, let me just write it first. Okay, let's take this up a bit and see what we can do. This is actually like plus k into something should be common. Minus is common for sure. Sine phi cos phi is common. So we have minus sine phi cos phi into, so if you take away minus sine phi cos phi from here, you have sine squared theta. Then plus, because minus is outside already, then you have cos squared theta. That's lovely because sine squared theta plus cos squared theta is actually 1. So this is the only thing we have left for k. So we have minus sine phi cos phi in the direction of k. So that is the cross products of r theta and r phi. That's all we have left for that. Okay. Yeah, I think that's it. So now all this, yeah, what can something still cancel here? We have minus sine squared phi cos theta I. Can we add something or so? Um 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 okay, now all those directions are like that. And sine phi k, how does this become sine phi k? So I guess there's a way that this whole thing simplifies to r theta cross r phi, and that is equal to sine phi k. I don't have a clear explanation for that at the moment, but because it looks like a tedious process because we have, okay, could it be about the movements? Okay, so in short, we have this coming from this whole place now, and that is a simplified version. So, and that takes us to step 4. I guess I'm gonna change marker now. Step 4. Step 4. And in step 4, we evaluate the vector field. Evaluate the vector field F on the surface. On the surface. So, talking about the surface now, we just have we have F of R, which is a function of theta and phi, and all that is equal to let's see, where did the surface start from? Okay, I think this is going to refer to this whole thing now, right? So F itself, right, is actually given by Zi, yeah, Zi plus Yj plus Xk. Zi, so we have to write the original R, right? And then we go in that order. Yes. So this is serious. So yeah, so this is what we need now, right? So, and that is always deriving from R. So so we can say we have from R theta phi, which is equal to sine phi cos theta I plus phi sine phi sine phi sine theta j plus cos phi k from that, right? And don't forget the original force field. the original force field we had says from the original force field, as we have f now of x, y, and z. See how the order is. So that means you have z in the direction of I plus y in the direction of j plus x in the direction of k. So if you want to follow this now, normally this should be x, So so x is going to come to k and y is going to come to j. So y remains in the right place, but then z is going to now be cos theta. Normally this should be x, y, z. So, but for the force field, as red is in the direction of I. So in that case, we can say that f of r of theta, phi, theta, phi is equal to cos phi I, okay? Because z is a zi. So cos phi I plus y, that remains. So we have sine phi cos theta j. And x, for x now we have plus sine phi cos theta in the direction of k. So that is the fourth step, which is about evaluating the vector field on the surface. So that is how that goes. So okay. All right. So we have so this is important again. Now that's step 4. So talking about step 5, this is lengthy indeed. So step 5, compute the dot product. Remember the formula itself. Compute the dot, compute the dot product. The dot product. So don't forget that this is actually F dot RU cross RV, or in this case, R theta cross R phi. Then D, that's now with D theta d phi, something like that. So to compute the dot product now, we have F dot R, that is F dot R theta cross R phi equals, so we have F itself is this plenty thing. So I think I'll just, okay, I guess I need to be patient to write that out. So, okay, yeah, we can do this. So F itself, right, is cos theta, cos phi I plus sine phi cos theta j plus sine phi cos theta k dots. We said in summary, r theta cross r phi sine phi k, sine phi k. You may want to confirm why that is that. Sine phi k. Okay. So since you are doing dot product, it makes everything even very simple because so this is sine phi k, right? So only k can go with k. Every other thing goes to 0. So this whole thing will just simply be sine squared phi. So that'll be sine squared phi cos theta. Okay. Yeah, that should be sine squared phi cos theta. So we're talking about k. So that should be sine squared phi cos theta. So we have sine squared phi cos theta. It's dot product now, so all that will go. I think at this point, I just want to jump to the final answer. Okay, so I'll just set up this. So we have step 6, step 6, step 6. Oh, that's not how to write 6, right? That's step VI, step 6. So we integrate over the surface, integrate over the surface. Integrate over the surface. And if we do that as in double integral over the surface, f dot ds, and that is, of course, this is now integral over the surface of f dot r theta plus r phi d phi d theta, So now we can put everything here. So that's integral, r is from, theta is from 0 to 2 pi. So we have 0 to 2 pi for theta. Then we have the other one is phi. So we have integral from 0 to pi over 2. So okay, I think I have a nice way of representing this so that you don't get confused which is which. So theta is from 0 to 2 pi. So we have theta equals 0 to 2 pi. Integral from phi equals 0 to pi over 2 of the final expression we got is sine squared phi cos theta, then d phi d theta. So if you evaluate this expression, you will get the final result. So I could as well leave it this way because it can be quite complicated. So in short, this now represents, so we can say this represents the flux of the vector field, the flux of the vector field F through the upper hemisphere, of the unit sphere. And that goes. Okay, so with this, we've come to the end of this long video. But I know it's worth it. So if you have not subscribed to this channel, be sure to do that. And do not forget to hit the notification bell so that when a new video is released, you can always get alerted. Then be sure to comment, like, and share always so that more and more people can have access to this. See you later. Bye.